semiconductor memory interfacing of RAM and ROM type. So there is a method what are the range of the memory location addresses inside the memory map. Now, what is the definition of the memory map? Memory map is a pictorial representations of an address range and shows where the different memory chips are located within the address range. So I have already told that the memory chips has a specification of its total size, that is total number of the unique locations, multiplied by the width of the data bus, that is a byte or number of bits. So for example, that means a particular memory block which has a size or address size of 1 kilo, which means a 1 kilo address location. Each address location can store the information on byte. So that is the specification of the memory chips. But the memory chips are available with the address signals, which is the input signals to the memory chips, the data bus signals, which is of bidirectional, that is, it is from input as well as from the output during the reading of the information from the address location. And the minimum number of the control signals which needs to enable the memory chip is a chip enable signal or chip select signal, which is normally active low, as well as the two other control input signals which are coming from the microprocessors is the read bar and the write bar. So these are the three important timing signals which under the actions of the the memory can be accessed by any CPU, that is 8085. So what is the interfacing method? That means, first of all, this 1 kilobytes, where it falls within the address map of the microprocessor. For 8085, the total size of the address map is 64 kilo. And the bottom address is 00 and the top address is all FFF. But how it has been partitioned, and each partition corresponds to each memory chip block. So that is much more important. So 1 kilobyte of memory chips can fall any one of this partition range or partitions, that is the address range. So we can see from this example, that means the top, that is a address space or the range of the address from starting from the 00 location to the 3 FFF hexadecimal. What is the size? Formula is the higher address minus the lower address plus 1, which is equal to the size of the total EEPROM, erasable programmable read-only memory chip size. What is the size of the RAM 1 chips? The address range is specified in the memory address map. The bottom address is 4400 hex and the top address is 5FFF. So what is the size? 5FFF minus 4400 plus 1. So that is the address range of the RAM 1 chip. Similarly, the address range of the RAM 2 chip is found in this manner, and the address range of the RAM 3, RAM 4 are equally determined in the similar line. Now, physically, the total number of the memory chips having the number of partitions will be size that the size of the sum of the size of the all partitions must be equal to the 64K, beyond which no memory chips can be interfaced or connected with the help of address data and the control signals. So that is the method. So you must understand how the memory can be interfaced with the help of input information, that is address range of the each chip or the size of the each chip and its relevance to the address map of the microprocessor or memory address map of the microprocessor. How that means address map is important, address map information is important, how the chip is located physically in respect of the address range onto the address map. So that's why this is a very conceptual thing, that is how the memory can be interfaced and according to the given information in the memory map. So same things will be applied in case of I/O interfacing, that will be discussed later. Now, how this timing and the control signals will be generated. 8085 has three important information or four important timing signal. One is called the ALE, address latch enable, I/O M bar, read bar, write bar. So with the help of four minimum timing and the control signals, the memory chip should be enabled or can be accessed. So what is the method to generate the control signals with the help of combination logic circuit? So this is a typical combination logic circuit which takes the three input signals coming from the 8085, but it will generate the four timing control signals. How four? Why four? Because for reading and the writing the memory chips, mem R, mem W bar and the mem R bar are needed. And for I/O devices, I/O R bar and the I/O W bars are needed. But the three are generated by the microprocessor itself, 8085. So how it can be done with the help of combination logic circuits? Four signals according to these logic gates. Similarly, this is not a unique, but there may be a different combination logic circuit according to the truth table. Now, what is the truth table? That means if the information over this signal that will be decoded or encoded, whatever may be, at the output lines. So based on this combination logic circuit using K-map method, Karnaugh map method, what will be the actual logic gate circuit that could be found out. So that means the input signals are three, but the outputs are four. Two of which are used for memory interfacing and the two of which are used for the I/O interfacing. So that is the techniques, how the control and the timing signals will be generated. Now, what is the address and the data bus interfacing with respect to the memory? We know the 8085 can produce higher order address signals over the A8, A15 lines, and the lower order address signals which are mixed with the data signals also, 8-bit data signal designated as AD0 to AD7. That means the lower order address lines and the signals are mixed, combined at a different, that means it has got a meaning at different time slot, that is the data bus. Why? That means it is called the address data multiplexing, because the lower order address line is 8 as well as the data width is 8. So these are mixed together, combined, but not at the same time, at a different time. So how it is needed, that means the lower order address data multiplex signals should be demultiplexed or separated with the help of combination logic circuit. So what is the technique? That's why a signal, timing signal is provided by the 8085 called address latch enable. That means with the help of the external combination logic circuit like latch, the lower order address signal must be stored or latched so that the output of the latch will retain the lower order address information. But there is no need to latch the higher order address signal over the A8 and A15 lines, as because it will be retained during the whole timing operation or the information fetching or information storing or information reading and writing to the memory location. So that 8085 with the help of this external latch can produce the total 16-bit address signal, and the lower order address then after separation will be designated as A0 and A7 strictly. It is not mixed with the data signal. But at a different time, as because the latch will retain the timing and the control signal, because the latching actions will occur when the ALE will produce a positive pulse. That will be discussed in detail about the machine cycles of an 8085. So once the lower order address signal has been latched with the help of the external latch, the lower order address information will be retained until and unless there will be occurrence of the next ALE pulse. So once the address information is latched over the latch, then the data bus will be free, and this data bus and this bus will be free for data access. So we can 8085 can read or write the data over these bus signals. So during addressing, it is an unidirectional, that means from microprocessor to the outside. But during the data access operation, it becomes bidirectional, the same address signals. And the data can flow over this bus to inside the microprocessor, or data can flow from the microprocessor inside the data bus via this. So this is called accessing the memory from the CPU, as well as accessing from I/O. So there is this diagram has an I/O and the memory along with the CPU, central processing unit. So that means this is very important information. That means how to generate the read and the write control signals for both memory and the I/O devices, and how the memory should be connected, interfaced with the help of the latch. So these are the two important techniques. These are written here. So this is a typical circuit diagram with the conditions of the ALE signals. That means when ALE become 1, latching will occur, as well as the bus will be lower order bus will be considered or treated as an address bus. But when ALE becomes 0, the lower order bus is that means this bus is utilized for data access. But the higher order address bus will be same. That will not be changed. So this circuit means how the address data bus are multiplexed or demultiplexed. So latch is acting as a demultiplexer. What is the meaning of the demultiplexer in combination logic circuit? To separate from the common input signal over the different lines or different output lines. What is multiplexer? Combine the separate input signals to a common signal. 8085 produces the multiplex address data signals over the lower order address bus designated as AD0 to AD7. So you must understand what is the meaning of address data multiplexing and the demultiplexing. Now, why it is done? Why address data information is passed by the microprocessor over this multiplexed data address data bus? If separate buses are used, then what will be the number of signal lines? That means 8 plus 8, 16. But with this address data multiplexing technique or method, 8 lines have been minimized. So it is become economic. Otherwise, the size of the 8085 CPU chip would be bigger. So that's why all CPU, generally the 8085 and the Intel CPU uses this method for multiplexing the address and the data bus to a common bus signal. So similarly, definitely there is a need, essential need for demultiplexing the address data information. Otherwise, the information about the address and the data bus will be mixed up. So how the memory location will be uniquely addressed with the help of the unique signal? This is not possible without demultiplexing. So that's why because the 8085 CPU generates the address data multiplex information, so there is a need to use the external demultiplexer, that is latch, to separate the signal over the two separate 8-bit lines. Now come to the how these memory blocks, that is 1 kilobyte of the memory chips, will be enabled according to the address range. So this is called the memory decoding, memory address decoding. What is that? What is the meaning of the memory address decoding? Address decoding refers to the way a CPU systems of the computer system decodes the addresses on the address bus to select the memory locations in one or more memory ICs or chips or peripheral devices. The different types of the address decoding techniques in microprocessor are absolute decoding or linear decoding or block decoding, first method, and the second method is called the partial decoding. Now, what is the difference between the absolute decoding and the partial decoding? Partial decoding. Suppose if we consider this diagram, shows a 64 kilobyte EEPROM, a memory chip. The chip number is 27512. Is to be interfaced with the 8085. So 64 kilobytes is the size. What will be the minimum? What is the number of the address lines? What will be the number of the address lines? According to the binary method, (64 kilobytes) means 16 lines, A0 to A15. So ultimately, this is the A0 to A15, 8 plus 8, make the 16 lines. So 16 lines will be connected to that, what these all lines. Let us take another good example. That means, so this is a good diagram. That means 4 blocks of the memory chips are to be interfaced with the 8085 with the help of the memory decoder. And so a demultiplexer, that is a latch, is required. And what is lower decoder? The selection of the output, that means the decoder has 4 output lines. It has 3 input lines. So ultimately, according to the information supplied by over these 3 address lines, which output lines will be selected? We can see what are the address lines which are given to the input of the decoder. A 13, 14, 15 designated. That is the most 3 significant lines are used for decoding the memory blocks or decoding the address range following of the memory block. So 4 chips are connected to the 4 output lines of the decoder. So according to the address information, that is the most 3 significant input line, which blocks will be enabled? That can be found out from this analysis of the truth table. So the first 8 kilobyte of the EEPROM, that is EEPROM 1 block, when all are zero over the A13 to A15 address lines, this block will be enabled. Means this line will go low, active low. All the lines will be at inactive high. When only A13 line will be 1, we can see the 8 kilobyte, there is another 8 kilobyte designated as the EEPROM 2 blocks will be selected. So other output lines will be inactive, only the Y1 bar line will be active low. Likewise, depending on the information over the least or most significant 3 lines, that is when the A13, A15 and A13 lines will assume this logic, A15 will be low, A13 and the A14 will be high. Then the last block, that is a RAM2 block, will be selected. That means, according to this information over the address signal, the memory chips will be selected according to the truth table. But the other address lines are directly interfaced, leaving A13, A14 and the A15. What are the rest of the address lines? A0 to A12. That means 13 address lines marked as this over the bus line 13. These are connected to the 8 kilobyte. And to uniquely address any location within this 8 kilobyte size of the EEPROM 1 block, only 13 address lines are required, not more than that. Because 2 to the power 13 is equal to 8 kilobyte. 8 kilo, you calculate. Similarly, for another equal size, that means 13 address lines will be required to select any one of the unique address location inside the block 2, that is EEPROM 2. So this will select the partition. This will select the decoder output, will select the which partition. And within the partition, the rest of the address lines will be utilized to point physically the memory address location. So what will be how the absolute address location after decoding? You can see the rest of the address lines information are shown, starting from the A0 to A11 or A12, which can change starting from the all 0 value to all 1 value in the respective row. Now, if we combine all this information over the 16 address line from the first row to the last row for the first block, what will be the physical address? In the address range, that will be 0000 to 1FFF. So this is the range of the address for the first partition of the first block. The next block has a partition in the range of 2000 hex to 3FFF hex. The size is what? This address minus the top address plus 1. You calculate, it will be 8K. So for equal size partition, this is very easier. The truth table must be given. You have to analyze the truth table. Accordingly, based on the truth table, you have to draw the interfacing diagram. Now, how much is the total memory space has been utilized by the 4 memory chips? 8 plus 8 plus 8 plus 8. That means 32 kilo address location are utilized, which maps onto the address map of the 8085. What is the address map size? 64 kilo. So out of 64 kilo, only 32 kilo locations are utilized. So what are the free locations? 64 minus 32 kilo, that is another 32 kilo physical locations are available to connect the further blocks of the memory ICs, so that the total 64 kilo location will be physically will be utilized. by physical interconnection. So that is the meaning of how the memory address space is decoded. This is a similar diagram. Consider a system in which the 32 kilo memory location space is implemented using phone number of the 8 kilo memory location. That is the next diagram. And the previous diagram has a problem like that. Consider a system in which available 64 kilo memory space is equally divided between the EEPROM and the RAM, each having 32. So this is the diagram. The truth table you have to draw. What will be the address range? That means based on this connection, what will be the outcome under truth table? So the problem, two general problems that under memory address decoding will be set. One is either you will be supplied to this truth table and you have to draw this physical diagram, or the physical diagram is given to you, you have to draw the truth table according to the address line connection. So that is the meaning of how the memory decoding and the memory decoding is very important. That means some of the address lines will be given to the connected to the memory address decoder. Here 2 to 4 address decoder, priority decoder, a logic circuit or logic gate has been utilized. So leaving this address line, the rest of the address lines will be directly connected to the memory block. A point should be remembered, that means we cannot connect 16 kilobyte location, as because in case of a 16 kilobyte location, additional A13 address lines will be required. So that will be a misnomer. So that is a technique. That means what will happen if we connect 16 kilobyte memory blocks? We require the further additional address line, that is A13, but A13 is utilized by the decoder. So should I connect the A13 to a common address line? Yes or no? That is the question to you. You must be able to answer. So this is another diagram interfacing phone number of the 8 kilobytes EEPROM and the phone numbers of the 8 kilobytes RAM with the 8085. So 8 into 4, 30 and 32 kilobytes. That means full 64 kilobytes has been utilized by this diagram, by this circuit diagram or memory interfacing. Here the size of the decoder is bigger. That means it will be 4:16 or 3:8. So all 3:8 means the number of decoded line is available 2 to the power 3, that is 8. All output lines are available. So these are the connection, these are truth tables. What is the address range following for each of the memory blocks, different types, EEPROM, RAM, etc. EEPROM, RAM, EEPROM, etc. So now the question is, I have told that is absolute decoding and partial decoding. What is the meaning of this? Absolute decoding is full decoding, address decoder. In case of a full address decoder, each memory location corresponds to one unique address. What is the meaning? So out of 64 kilo size location, each location is designated by the hexadecimal number, that is unique address. No don't care address bus. That means no address line can assume either 0 or 1, that is don't care. In that manner, the connection would be like that. But that means, is it possible that we suppose in this example, we can see a decoder has been used, which is a NAND gate, 4-input NAND gate. The input address signals are A12 to A15. So what are the rest of address lines? A0 to A11. But we have to connect 2048 means what? 2 kilo. 2 kilo size 4-bit address lines, not 8-bit. Anyway, forget about the data bus, it may be 8-bit. So 2 kilo, which are the same, which require the same number of the address line, A0 to A10. So 11 address lines are required to point the physical location. But this block of partition should be selected by the decoder output, which has common, that means the diagram shows that means 4-bit and the 4-bit, which combines the 8 data location, 8-bit data location. So both have a common chip select lines. So when the chip select will be selected, that means according to the input output truth table condition. That means when all the signals over A13 to A15 will be all high, then it will be selected. So we can write the most significant 4 lines all 111, and we have to write the rest of the address lines assume that all 0 and then all high. So we can get the range of address for this diagram is how much? The 4 nibble comma F, that is F000 to F7FF. Because the A11 address lines is don't care. It may be high, it may be low. There is no connections. There is no connections from the CPU to any one of these memory blocks utilizing A11 line. So A11 is left open or floated or no connection. So A11 can assume either 0 or 1. This does not at all affect the decoding. The blocks will be selected, that means for the physical address range of F1000 to F7FF, or there will be another duplicate address that is all FFF. That means if the A11 becomes high, first of all, if the A11 is 0, that is the top address, A7FF. But if we assume the A11 is high, then the top address will be FFFF, all FF. Which means without connecting the A11 address signal lines, the range of the address is not unique. It will be redundant. That means either these blocks will fall in the address map of F1000 to F7FF, or it will fall when the A11 will be 1. Considering A11 is 1, then the list address will change. Definitely it will not be F1000. It will be 1. How much? Because it will be F800. When A11 will be high, please check the lower address range will be F8000 and the top address will be all FFF. So the number of range will be duplicate without connecting, not considering the A11 line. This is an example of the partial memory decoding. In case of a partial decoding in which all available address lines, that is 16 lines in the memory mapping and the 8 lines in the memory peripheral, are not used for decoding, resulting in multiple addresses for the same range at same port. And this is called the partial decoding. But in case of a full decoding, if we convert it to a full decoding scheme, then we must use the A11 line to the decoder address, decoder input signal, which will be a 5-input NAND gate. Try to understand. So in that case, only one range physically signified will be signified. But here, the two blocks of range will be physically signified, but there is no physical location through separate location really. So the same hardware connections, there will be two different range. One range is F1000 to F7FF, another range is F800 up to all FFF. That means after partial decoding, the full memory address spaces are not utilized. So there will be an image formation, there will be image addressing. That means with partial decoding, the memory space will be lost. It cannot be utilized because if we do not select the A address line, you can see there will be formations of the image address. Original address has got a F1000 to F7FF and the image will have a F800 to FFF. But there is no really the physical space within this range, F800 to FFF, because F800 and the F1000 are the common locations. So this is highly undesired. So the result of the partial decoding is to make the wasting of the memory address space. But what is the advantage of the partial decoding? The less complexity of the connection will be connected. A11 is not required to be connected to anywhere, neither to the memory address input line nor to the input lines of the decoder. So, did you follow this concept? Very important concept of memory decoding scheme. In terms, memory decoding two methods, that is absolute decoding and the partial decoding. What is the advantage of the absolute decoding? That means memory space will not be wasted. It can be fully utilized. But no address signals lines will be left open. It must be utilized. But by partial decoding, memory address space will be wasted due to the formation of the image address in the address map. At the same time, lesser number of the address lines will be connected. So these are the two advantage and the disadvantage in respect of the partial decoding and the full decoding. So there are different examples. Go through the example in the note. Examples of the absolute decoding as well as the linear decoding and the partial decoding. So that means the design problems generally are set in the exam. That means it will be given to interface the systems, memory systems with 32 kilobytes falling in the address range. Address range will be given. Draw the connection diagram and the truth table. So this is the problem in respect of the under memory decoding scheme. Now, did you understand what I have said? That means, what is the meaning of the memory decoding? Hello? Or you find any difficulty to understand this? This is a conceptual thing. It is not like that you read mechanically, but you have to understand. For that, you must follow the digital logic or combination logic, decoder logic. So I am going to the next part. which is very important. That is machine cycles of CPU. What is the meaning of the machine cycle? That means already it is known the CPU will work in steps of definite time slots. So the purpose of the CPU to execute the instruction, execute the program in the form of the written in the form of the instruction. So that's why reading instruction should be decoded so that appropriate timing and the control signal will be generated by its internal timing and the control unit. We have seen that in the architecture, there is a internal architecture of the 8085. So the every instruction will generate the appropriate timing and control signals in the form of machine cycles. So the machine cycles is very important. So what will be the time allocated time slots to execute a particular instruction or given instruction? That's why the manufacturer has assigned a definite time slot, which are called the machine cycles of CPU. And they are classified according to the nature of how the timing signals will be generated. First of all, according to the timing diagram, so this is the timing diagram. And the right half, what is the top signal? That is the basic timings and clock, basic timing signal called the clock signal or clock out signal. And we can see that each period of the clock signal are designated with called the timing states called T states, like T1, T3, T4, and so on. So in respect of the clock signal, how the address, data, ALE, IOM bar, read bar, write bar signal will proceed. What are the active states and the inactive states? These are designed. So the whole set is called the machine cycles. Not only the fundamental clock cycles, but along with the clock cycles signals, the other transition states of the all relevant signals that may include the address and the data bus as well as the control signals must be displayed in the form of the waveform, and this waveform is called the timing waveform or timing diagram. So what are the classifications of these machine cycles? How they are classified? The name of the machine cycles according to the transitions, logical transitions, are called opcode fetch, memory read, memory write, IO read, IO write, interrupt acknowledge, bus idle. So 8085 has 7 types of the machine cycles. Each and every instruction may combine, maybe a combination of these 7 machine cycles. Not all, maybe 3 combination or 2 combination like that. What is meant by the opcode fetch cycle? Alternately, opcode fetch cycle is the first machine cycle designated as M1 machine cycle. Each machine cycles may utilize a fewer number of the timing states like T1, T2, T3, T4 relative order. So that opcode fetch is called the M1 machine cycles. So this is the diagram of opcode phase machine cycles or M1 machine cycles. And these machine cycles have been described by the following steps. For example, the step 1 means timing states 1. What will happen over this first clock period or first clock cycles? These are first clock cycles of the M1 or opcode phase cycles. So what will happen over the T1 state? In T1 state, the 8085 places the content of the program counter. What is the length of the program counter? 16 bit. So 16-bit address will be placed by the 8085 over the address bus. The higher address byte of the program counter is placed on the A8, A15 lines. And the lower order byte of the program counter is placed on the 80 and the 87 lines. The 80 and the 87 lines are called the multiplex address data bus. And all this information will stay for this whole clock period, that is T1 states. Thus, microprocessor activates ALE address latch enabled signal, that is a timing control signal, which is used to latch the address byte in the external latch before it disappears. Now see, that means over the T1 states, the ALE signal will be pulsed of this duration. But over the following T states of the machine cycles, M1 machine cycle, there is no transition of the ALE signal, which means only this time is allowed or allocated so that the lower order address signals will be latched with the help of the external latch. At the same time, over the T1 states, either IO M bar, that is another important timing signal, may undergo high or low. Otherwise, it will be in the floating state. This is the indication. So this level is the low logic. This level is the high logic. And over the whole machine cycle, that is M1, it will be either high or it will be either low. That depends on whether the memory is accessed or whether the IO is accessed. And at the same time, opcode phase cycles means the opcode which is stored inside the address memory location, that has to be read by the microprocessor and will be placed to the instruction decoder or internal registers or whatever may be. So that's why read bar signals is required. But the read bar signals will be activated following the transition high to low, and it will stay for this active state of this duration, which falls in the midway of the T2 second T states to the midway of the T3 T states, and it will disappear. So this is controlled by the internal architecture of the 8085. User cannot change these things as manufacturer, as specified by the manufacturer. So this is the whole phase of the transition diagram over the first machine cycle. And this diagram is what will happen over the each T states when the data and this flow that is indicated. Figure is data opcode flow from the memory to microprocessor. Memory lies external to the microprocessor, but this diagram resides inside the microprocessor internal architecture. So this is the timing diagram. This is the data flow diagram. And also the step 2 means, that means T2 states, what will happen? The low order address disappears. See, low order address appears over the T1 states. This will be latched. But over T2 and the T3, that means over this inactive state, high impedance state, low order address will disappear. That's why it will be at a high logic state. Then at the middle point of the T2 state, these signals will be utilized for accessing the data or opcode. Opcode means which will flow to the data. Again, it will disappear to high impedance states after the end or middle of the T stage, and it will be at high impedance stage up to the end of the machine cycles, T4 states. So that is written. So you have to understand what are the operation or micro operation which are defined under the different steps. T steps 2, step 3, step 4. So step 4 is the actions taken by the microprocessor over the T4 states. For example, a typical microprocessor instruction in assembly language or machine language, or not machine language, assembly language, means move A, comma B. That means the instruction indicates the content of the register content. B register will be moved to the A register. Similarly, there are different instructions which has its own machine cycles. But the opcode fetch cycles means related to this instruction, that will be common for all types of the instruction. But the machine cycles may consist of at least in one cycle, that is opcode fetch cycles mandatorily, and the subsequent machine cycles which may be classified among the other 6 types of the machine cycle, like memory read, memory write, IO read, IO write, etc. So the machine cycles is not only the opcode fetch cycles, it is a part of the complete machine cycles which is designated as the M1. But there must be some M2, M3 machine cycles which must not be opcode cycles, because opcode cycles will occur uniquely one time. The following proceeding machine cycles will not be opcode, but it will be some other. For example, it will be memory read cycles, memory write cycles, IO read cycles, IO write cycles, etc. So these are the description. That means what will happen in case of a memory read cycles. Memory read cycles will consume how much timing states. You can find the difference for memory read cycles and memory write cycles. Both only 3 T states or timing states are allowed. But in case of a opcode fetch cycle, additional timing states is required, that is T4 states. But in case of a memory read and write operation, the second cycle will be memory read and write, that is M2 cycle. That will utilize only 3 T states. And this is the diagram, timing diagram and the data flow diagram. This is also for memory write cycle. This is almost same, except there is for memory read cycle only there will be transition over the read bar, but in case of a memory write cycle there will be transitions of the write bar. Read bar will be at inactive states. Here also the write bar is not shown, but it will be at inactive or high impedance states. So try to understand the concept of the machine cycles also. Machine cycles give you the insight how the instruction will be executed by the CPU with the help of its internal architecture and the timing control unit. So try to follow, understand. If you do not follow, then if any doubts in your mind in this, you may ask the question. Otherwise, if you cannot understand the machine cycles, instruction cycles of a CPU, you cannot proceed further for interfacing the peripherals, IO devices, and for writing the program. So this is very important part of the course, that means to understand about the memory IO interfacing and the concept of fundamental idea of instruction cycles or machine cycles. After machine cycles, within the main cycles, we will go to the classification of the microprocessor instruction. So these 3 modules are very much important: internal architecture, memory IO interfacing, and the machine cycles, and the classification of the instruction. The rest are only the application of those. Did you understand what I have said? Hello? Did you follow? Or if you any doubt, please doubt in that respect. You can ask question. Can you follow what I have explained so far?
Yes, sir.
Please read thoroughly about the machine cycles or instruction cycles, as well as the memory decoding. I have already sent the e-notes on this part, memory interfacing and the instruction cycles to the Google Drive. Have you got the share link? Please download this material. If not, download the material from the share link. I have also supplied the share link. Send the share link.
স্যার এই নোটগুলো কি সব এনপিটিএল এর?
কোনটা? না, সবটা এনপিটিএল এর না, অনেক বই থেকে নেওয়া আছে, অনেক ইয়ে থেকে সোর্স থেকে নেওয়া আছে, গ্রাউন্ড থেকে নেওয়া আছে। মেমোরি পার্টটা এনপিটিএল থেকে নেওয়া।
আচ্ছা স্যার।
টাইপস অফ ক্লাসিফিকেশন অফ দ্য মেমোরি এগুলো এনপিটিএল থেকে নেওয়া। আদার থেকে নেওয়া আছে আমি দেখে বলছি, কিছু কিছু আছে, এগুলো এনপিটিএল এর না, যেগুলো দেখাচ্ছি এখন এগুলো সব দিয়ে দিয়েছি। এর কিছু পার্ট পড়েছে, এইগুলো মনে হয় এনপিটিএল থেকে। These are NPTEL description. These are good. OFMC means opcode fetch machine cycle in abbreviation. These are the e-notes available from NPTEL. যেগুলো দিয়েছি around machine cycles. So these are the important handout. All are described. You need not consult any. Even this part is not well defined in Ramesh Gaonkar book. Ramesh Gaonkar book is famous for programming and other things. But theoretical concept is better if you are conversant with the timing states diagram. Sometimes I do not know whether you become familiar about the state transition diagram in digital logic circuit. So this is one way to represent the working of the sequential logic circuit with the help of state transition diagram. So state transition diagram is an activity node as shown by the round symbol, within which what will happen in the T states or timing states. Here also, in case of a microprocessor, that is the first T1 states, what will happen, and it will proceed to the next state, so that the state transition diagram of a machine cycles is represented by state transition diagram. So each machine cycles or each type of instruction can also be represented with the help of STG diagram. That means what is happening inside the microprocessor, it will be clear to you. But I think the concept or the understanding about the state transition diagram will be clear when you will complete the theoretical study of the sequential logic circuit. So this is not required, but still the NPTEL lecture covers up so many advanced topics. So these are lecture 16, 17, 18. This is also a state transition diagram, some things equivalent to the flow diagram or flow chart. But in case of flowchart, there is a decision part or legend. Anyway, if you are interested, then you can go through the state transition diagram. Not right now. First, you clear your basic concept. Then you'll be familiar about this. And these notes I am just illustrating right now. But there are other better notes are available under the machine cycle instruction. The whole module is instruction cycles called. So these are the next part is the instruction classification of the instruction. This I will follow from the NTPL or NPTL. But we have covered introduction to microprocessor. We have covered just now memory decoding. And we have covered memory, that is theory of semiconductor memory, like that, static RAM. Again, we will further discuss about the material technology, how the memory has been built. So we have covered, I think, 3 modules today, as on today. So today we can leave. So in the next class we'll start from the instruction classification of the instruction of the CPU. Okay. Hello.
Yes, sir.
Is it enough?
Yes, sir.
Or we will proceed to the instruction classification? I think it will be not suitable for you right now. So today I am leaving. Okay.